Hello students, in this lesson today we are going to learn new lesson, and that one is there, fourth lesson is there, effects of electric current. So in that effects of electric current, before this we have studied there are three effects of electric current: heating effect of electric current, chemical effect of electric current, and magnetic effect of electric current. So there are different effects of electric current. So before this, some questions are there. Before starting the lesson, some questions are there, and that question is there. First question is there: how do we decide that given material is good conductor of electricity or insulator? How do we decide given material is good conductor or insulator? So if you will conduct that, if you will connect that particular component, that particular material between two terminals of the cell, and if you will connect it in the circuit, and if electric current flows through it, if a bulb will glow, then you can say that one is good conductor of electricity. Second question is there: iron is good conductor of electricity. Iron is good conductor of electricity, but when we are touching to the piece of the iron resting on the ground, if that piece of the iron is falling on the ground, resting on the ground, and if you are touching, then why we don't get electric shock? Why don't we get electric shock? So when that object is lying on the ground, at that time, whatever, if that object is charged, that charge is flowing to the ground, and that charge or that object becomes chargeless, charge is transferred, so that iron object which is falling on the ground, it is not having any kind of charge, so we are not getting electric shock. Next thing is there, before starting the lesson we have to revise some concept, and that concepts are there. First concept is there, static electricity. Static electricity. Before this we have studied static electricity. So that electricity which is existing between charge and uncharged object. That a charge which is, or that electricity which is existing between charge and uncharged object, or that electricity which is stored at one place, it is called as a static electricity. So example is there: if you rub plastic scale on the hairs, and if you take that particular scale near to the pieces of paper, then that pieces of paper gets attracted. That one is also one of the example of static electricity. Another example is there: if you rub a balloon, if you rub the balloon and if you stick to the wall, that balloon stick to the wall because balloon is charged and wall is uncharged. So there is force of attraction between charged object and uncharged object. Force of attraction between charged and uncharged object, and so that particular electricity existing, or electricity stored at one place, or it is existing between charged and uncharged object, it is called as static electricity. Next thing is there, and how that particular charge is produced, or how that charge is transferred. So charge production, in that three ways are there. Transfer of charge there, in that three ways are there. First one is there by friction, second one is by conduction, and third one is by induction. So when you are doing friction between two objects, then object get charged, and that charge can be transferred, or charge is produced by friction. And the second one is the conduction. If you are taking, suppose two objects are there, one is a charged object and another one is there uncharged object. If you are touching the charged object and uncharged object here, then charge will get transferred from this charged object to the uncharged object. Charge will get transferred from charged object to uncharged object. And an induction is there. Suppose this object is there charged, this object is there uncharged, and suppose here positive charges are there, and here negative charges are there. Here positive charge, here negative charge, here positive charge. So there is force of attraction between positive and negative charges, and charge will get transferred. Charge will get pulled here. So here electrons, from here electrons will be pulled this direction, and here positive charge will become. So how charge is transferred? Transfer of charge production and transfer of charge, and in that these three ways are there: transfer of charge by friction, conduction and induction. So after this next term is there, and these are most important terms. In that, first one is there potential difference. Some terms we are going to revise, and that terms are there. These terms we have studied in the current electricity, last year. So first concept is there potential difference. So you are saying V, voltage, potential difference. So what is the potential difference? Amount of work done to carry a unit positive charge from a point of higher potential to lower potential. Amount of work done to carry or to transfer a unit positive charge from a point of higher potential to a point of lower potential. Is called potential difference. Or simply in case of electric cell, you can say difference in the potentials between two terminals of a cell. Difference in the potentials of two terminals of a cell. It is also called as potential difference. And potential difference is equal to work done upon charge, and it is equal to work done W and charge is Q. Potential difference is there. Suppose, and that potential difference we are taking voltage V is equal to W, and that W is there in the Joule. Work done is there in the Joule. So 1 volt is equal to 1 Joule upon 1 Coulomb. 1 Joule upon 1 Coulomb. So 1 volt potential difference is equal to 1 Joule upon 1 Coulomb. And you can do the definition of 1 volt also. So potential difference is said to be 1 volt. Potential difference is said to be 1 volt when 1 Joule work is done to carry 1 Coulomb charge from a point of higher potential to lower potential. So you can say 1 volt is equal to 1 Joule upon 1 Coulomb. So 1 volt is equal to 1 Joule upon 1 Coulomb. So this is term potential difference, and next term we are going to learn, and that term is their current, electric current. Next term is their electric current. In case of electric current, and it is denoted by I. So what is the electric current? Before this also we have studied, just we are revising that particular points because these points are important for understanding next part. So amount of charge flowing through a conductor in unit time, or charge flowing through the conductor in unit time or per second. Charge flowing, amount of charge flowing through the conductor per second, it is called as a electric current. So definition is there: amount of charge flowing through a conductor, amount of charge flowing through a conductor in unit time is called electric current. Or another definition is there: charge flowing through a conductor per second is called electric current. So an electric current, it is denoted by letter I. So electric current is equal to charge upon time. So current I is equal to charge upon time, and charge is Q and time is the T. So charge you are measuring in coulomb and time in second. So 1 ampere current is equal to 1 coulomb per second. If 1 coulomb charge flows in 1 second, then current is there 1 ampere. So definition of 1 ampere also you can do. Current is said to be 1 ampere when 1 coulomb charge flows through the conductor or through the circuit in 1 second. If 1 coulomb charge flows through the conductor in 1 second, then you are saying this one is there 1 ampere. So what you can do, 1 ampere is equal to 1 coulomb divided by 1 second. And ampere is the unit of electric current. Ampere is unit of electric current. Ampere is unit of electric current. So this concept you have to remember, because I is equal to Q upon T. This one also we have to use in Joules law of heating. Next thing is there, next term is there electric power. Next term is there electric power. What is electric power, or just simply power? What is the power? Last year we studied power is power is work done in unit time. Work done in unit time. So next thing is the electric power. Just power also you can say. So rate of doing work is called also power. Rate of doing work is also called as a power, or work done in per second, it is also called as a power. Rate of doing work. Rate of doing work is called power. Or work done per second is also called as power. So what is power? Power is equal to power P is equal to work done divided by time. Work done divided by time. So power is equal to W upon T. But your power unit will be there. You will find unit. So work done is there in joule and time is there in second. So power or electric power, or you can say power is equal to power P is equal to, and unit is there joule per second, you are saying watt is equal to 1 watt. So what you can say, 1 watt is equal to 1 joule upon 1 second. So power P is equal to W upon T. This one you have to remember, or W is equal to P into T. This one you have to remember. These relations we have to use. After this, one more thing we have learned, and that one is there. One more thing, that one is the Ohm's law. Ohm's law we have studied. Next term is the Ohm's law. So what is Ohm's law? So you have to obtain this relation, or one relation is that V is equal to IR. V is equal to IR. So statement you have to remember. If physical state of conductor remains constant, which are the physical states? Area of cross section, length of the conductor, material of the conductor, and temperature. Length, area, material, and temperature. If these physical conditions of the conductors remains constant, then current flowing through the conductor is directly proportional to potential difference applied across its two terminals. So statement we will write, if physical states of a conductor remains constant, then current flowing through a conductor is directly proportional to potential difference applied across its terminals or two ends. And so according to this law, V is equal to IR, or I is equal to V upon R, or R is equal to V upon I. These three relations you have to remember. So V is equal to IR, I is equal to V upon R, and R is equal to V upon I. These things you have to remember. So after this, actually we are going to start, and one more thing is there, resistance. One more term is there, resistance. So what is the resistance? Opposition to the flow of electrons, or hindrance to the flow of electrons. It is called as a resistance. Opposition or hindrance to the flow of electrons, is called in the circuit is called resistance. And the unit of resistance is there. Unit is Ohm, and the symbol is there like this. So these things you have to remember. So after this, next point we are going to learn, and that next point is the transfer of an heat or electric transfer of heat in electric circuit. What you can say, transfer of heat in the electric circuit. Next point we are going to learn, and that one is there, or before this point, 2-3 diagrams are given in the textbook, and on that diagrams, look the diagrams and discuss. This point is given. So if you look the diagrams, in that one electric fan is there, one electric bell is there, and in the house television is on. And see, these pictures are showing there are different effects of electric current. If you take electric bell, in that magnetic effect of electric current is there. If you take an electric fan, electrical energy is converted into mechanical energy. And if you consider electric bulb or television, in that electrical energy is converted into light. It is converted into light. Okay, so these are the effects of electric current. So we are going to learn energy transfer in an electric circuit. Next point is there, energy transfer in an electric circuit. So and in this we are going to derive one expression, and that expression is there, Joules law of heating. That one is there, Joules law of heating. In this, firstly we will draw the diagram, and then expression we will find. So electric circuit we have studied before this last year. So one battery or cell you will take, then in this you are connecting one key. After key, point A is there, and here point B is there. Between point A and B, you are connecting one resistor of resistance R. After this, you are connecting one ammeter. And across this resistor, you are going to connect one voltmeter. And here VAB will be the potential difference. This VAB will be the potential difference across resistor R. Resistor. Suppose current is flowing from positive to negative, and suppose charge Q is also flowing through this. Suppose charge is there Q, it is flowing from point A to B. Charge is Q, it is flowing from point A to B. Point A is connected to the positive terminal of the cell, and point B is connected to the negative terminal of cell. And point A is at the higher potential, point B is at the lower potential. So charge will flow from point A to B, from higher potential to lower potential. So like this diagram is there, and if you look complete electric circuit, if you will make switch on, electric current will flow, charge will flow, and because that electric current will flow. So in this you have to suppose different things. First thing is there, what you can say, suppose a resistor of resistance R is connected between 2 points A and B. Second thing is, suppose Q is the charge flowing through the resistor or through the circuit. I is the current flowing through the resistor or circuit. So again one more thing is there, VAB, it is the potential difference between points A and B. Again, next third point we are going to say point A. Point A is at higher potential and point B is at lower potential. Now so potential difference, next thing we will say potential difference VAB is equal to what you can say, work done upon charge. So VAB is the potential difference when the charge flows from A to B, and for that work is done, W. So what you can say, VAB is equal to W upon Q. But this work done, so therefore work done is equal to VAB into Q. Work done is equal to VAB into Q. Now another thing is there here, one more thing we can determine, we can say power is equal to W upon T. Power is equal to W upon T, work done upon time T. So according to this, power is equal to, this one is their work done. Suppose this one is their equation number 1 and this one is their equation number 2. From equation number 1, putting the value of W in equation number 2, what you can say, putting W is equal to VAB into Q in equation 2. So what you will get, P is equal to VAB into Q upon time T. But we know Q upon time T. So since I is equal to Q upon T, so what you can say, P is equal to VAB into I. And suppose this one is equation number 3. This one is the equation number 3. So after this, again one more thing is there, P is equal to W upon T. Therefore W is equal to PT. So putting the value of P in equation number, suppose this one is there equation number 4. If you put value of P in equation number 4, then you will get VAB into VABI into T. So putting P is equal to VAB into I in equation number 4, we will get W is equal to VAB into I into T. So after this, one more thing is that we are knowing this VAB means according to Ohm's law, V is equal to IR. V is equal to IR. So what you can write here, VAB instead of VAB, IR into I into T, and it is equal to, now this W is equal to this, it is equal to what you can write, I square RT, I square RT, and this H is equal to W is equal to this equation will be there, I square RT. So in this is our Joules law of heating. This is Joules law of heating. So 2-3 things are there, that on that only we have to focus. So whatever work done is there, when current flows through the circuit, when current charge will flow through the resistance, a resistor of resistance R, A to B, at that time work is done, and that W is equal to H is equal to I square RT, and this work done is energy produced, and this energy is exchanged, energy produced, and this energy is exchanged with environment. It is released into the environment, or it is exchanged with environment. So like this way, when electric current flows through the conductor or a resistor, heat is produced, and that heat is exchanged with the environment. So one more time we'll see this one, this equation. So one thing is there clear here, battery or cell is there, then a key is there, then in between A and B, resistance of resistor of resistance R is connected, V is voltmeter, A is ammeter, VAB is the potential difference, and if you are connecting a resistor of resistance R between point A and B, Q is the charge flowing through the resistor, I is the current flowing through the resistor, VAB is the potential difference across between 2 points A and B. At point P, potential is higher, at point A, potential is higher, at point B, potential is lower, potential is there. Potential difference is equal to, we are knowing, VAB is equal to work done upon charge. So VAB is equal to W upon Q, and W is equal to, if you will rearrange this one, W is equal to, this Q will go to this side, so W is equal to VAB into Q, equation number 1. Power, next thing is there P, fifth point is there, power P is equal to W upon T, work done upon time T, equation number 2nd, and it will keep value of W in equation number 2. So W is equal to VAB into Q in equation number 2, then we will get P is equal to VAB into Q upon T. So P is equal to V, but Q upon T is current. So P is equal to VAB into I, equation number 3, and if again if you put, if you consider 6 point, P is equal to W upon T, and W is equal to PT, this T will go this side, so you will get 4th equation, and putting value of P from equation number 3 in equation 4, you will get W is equal to VAB I into T. But we are knowing V is equal to IR, and if you keep this value of V is equal to IR in equation number, in this equation, then you will get H is equal to W is equal to I R into I into T, I square RT, and finally this equation I would write again, I would write here again, H is equal to W is equal to, what you are going to put, I R into T, and you will get I square RT, and H is equal to I square RT. This is the I square RT. This is Joules law of heating. Joules law of heating. All, I think you have understood this one. All I am going to rub, and in short only I am going to show this derivation. So I will rough all, and then in short I will tell how to obtain the derivation. Okay, so points you can write, these points you can write. but in short we'll see how to write, how to obtain that equation, because in one time only it is not. If you are paying attention properly, you can understand. If you will not pay attention properly, you will not understand. So in one thing is there, R is the resistance of a resistor. VAB, potential difference across A and B, between A and B. Then I is current flowing through a resistor or conductor. Then next thing is there, VAB over, then I, R. Now pay attention. So we are knowing first thing, potential difference. Potential difference. V is equal to W upon Q, and here VAB is there. VAB is equal to W upon Q, and W means work done. W means work done. So what you can write? Work done. To carry charge from A to B, to transfer charge from A to B, that work done is equal to VAB into Q. VAB into Q. So another thing is there, and this work is done to carry the charge, and when charge is flowing at that time, heat is produced, and that heat is exchanged with the environment. That heat is exchanged with the environment. So one more important thing is there, we are knowing power. Power is equal to P is equal to W upon T. So one more thing, suppose this equation number is there 1, this equation number is there 2, and if you putting W is equal to VAB into Q in equation second, then you will get power is equal to VAB into Q upon time T. But this QT, we know, since I is equal to Q upon time T, so you have to keep here I. So you will get P is equal to VAB into I. Suppose this equation number is there 3. Again, another thing is there, power is equal to P is equal to W upon T, and therefore W is equal to PT. W is equal to PT. So suppose this equation number is therefore putting P is equal to VAB into I in equation number 4 from equation number 3. So W is equal to what we will get? P's value from here. So VAB into I into T. Again we are knowing Ohm's law. Ohm's law. What is Ohm's law? V is equal to IR. So VAB is equal to IR, you can put. So VAB is equal to IR into R into T. So I into I square, and this R and into T. So W is equal to H is equal to I square RT. H is equal to I square RT. So this is Joules law of heating. Joules law of heating. W means work done, and work done means heat produced when charge flows from A to B. So after this, another one more thing is that I is equal to, as like V is equal to IR, so I is equal to VAB upon R. If you put these values, this value here, then you will get H is equal to W is equal to, instead of I square, VAB square upon uh, VAB square upon R square into R into T. So R and R will get cancelled and you will get VAB square T upon R. VAB square T upon R. So H is equal to I square RT is equal to VAB square T upon R. So this one is Joules law of heating. Joules law of heating. This one is the Joules law of heating. So study this one again and again, because just formulas only we are rearranging. It is very easy to understand. It is very easy to understand. So after this one is the Joules law of heating, and H means heat produced. When charge flows from point A to B, at that time heat is produced, energy is produced, and that heat is released into the environment. So after this we are going to write Joules law of heating. What is the Joules law of heating statement? So with the help of this equation only you can write Joules law. So if current I is flowing through the conductor of resistors, resistor of the resistance R for time t, at that time heat produced is directly proportional to square of current. Also it is directly proportional to the resistance of the resistor and directly proportional to time for which it is flowing. So that Joules law will write here. After this Joules law will write. From that equation only we can write Joules law of heating. So next term is there Joules law of heating, and what is our equation? H is equal to I square RT. From this you can write statement. We will write statement. If current I flows through a resistor of resistance R in time t, in time small t. If current flows, current you can say current I flows. If current I flows through a resistor of resistance R in time t, then heat produced in the conductor or resistor is, first thing is there directly proportional to square of current, or directly proportional to I square of current. Second thing is there directly proportional to resistance R. And third point is there directly proportional to time t for which it is flowing. Time, how much time it is flowing, time for which it is flowing. So this is statement of Joules law of heating. After this, next concept we are going to learn, and that next concept is there units of electric power. Next one is the unit of electric power. Unit of electric power. What is Joules law of heating? If current I flows through a conductor or through a resistor of resistance R for time t, then heat produced by the conductor or resistor is directly proportional to square of current, directly proportional to resistance of the resistor, and directly proportional to time for which it is flowing. So next term is the unit of electric power. Unit of electric power. So in case of electric power, power is equal to what you are saying, V into I, VAB into I. One equation we have seen, power is equal to VAB into I, VI. So power is equal to volt multiplied by ampere. So volt is the 1 joule upon 1 coulomb multiplied by ampere 1 coulomb upon 1 second. So this coulomb will get cancelled and it will remain 1 joule upon 1 second. And so power, electric power, unit of electric power P is 1 joule per second, means it is 1 watt. It is 1 watt. So 1 watt is equal to 1 joule upon 1 second. So when you are saying 1 watt, when 1 joule work is done in 1 second, then our power will be the 1 watt. Electric power is there 1 watt. So after this commercial unit of electric power, commercial unit of electric power. So if you see electricity bill of your house, then in that units are given, 10 units, 5 units, that much is there, and on that unit bill will be there. So that one we are going to learn. First thing is there, watt is smaller unit. 1 watt is small unit of electricity. Second thing is there, so if you will go to count this one, it will be in the thousand watts, many thousand watts. So instead of that one, we are taking larger unit, and that larger unit is the kilowatt. So instead of this one, we are using 1 kilowatt. 1 kilowatt as a larger unit, of electricity power. So 1 kilowatt is equal to 1000 watt. 1 kilowatt is equal to 1000 watt. Suppose if 1 kilowatt power is used in 1 hour, if it is used in 1 hour, then 1 kilowatt energy is used. 1 kilowatt energy is used in 1 hour. Then unit for electric power, or for that, then electric energy used is equal to, electrical energy used is equal to 1 kilowatt multiplied by 1 hour. So 1 kilowatt multiplied by 1 hour. So it is equal to, So how this one came? Because power is equal to W upon T. Power is equal to W upon T, and this work done is the energy used. This energy used, W is equal to work done or energy used or heat produced. This one is equal to, it is equal to 1000 watt multiplied by, in 1 hour how many seconds are there? 3600 seconds are there. So 1 2 3 4 5, 36 into 10 raised to 5 watt multiplied by second. So if you move one decimal point here, then it will become 3.6 into 10 raised to 6 watt second, and this watt second, it unit will be there. It is equal to 3.6 into 10 raised to 6 joule. So 1 kilowatt hour is equal to 1 kilowatt hour is equal to 3.6 into 10 raised to 6 in joule, and this one is called as a 1 unit. 1 unit is equal to 3.6 into 10 raised to 6 joule. This is unit used for the electric bills. It is used for electric bills. So watt is smaller unit of the power. So kilowatt hour, you are using larger unit for that particular energy or power. The next one is there, 1 kilowatt hour is equal to 1000 watt, and if 1 kilowatt hour power is used in 1 second, then electric energy produced or energy produced, heat produced, W is equal to PT. P means power, 1 kilowatt. T means time. So 1 kilowatt, 1000 into 3600, 36 into 10 raised to 5 watt second. So 3.6 into 10 raised to 6 watt second, and it will be 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule, and 1 unit is 3.6 into 10 raised to 6 joule. So this is unit used for electricity bills. Another thing is there, after this we are going to learn next concept, and that one is there, heating effect of electric current. Heating effect of electric current. So that heating effect of electric current, overloading, short circuit, these points are there. So after this, in next video we'll study these points. Okay.